In the previous video from 9.5, we saw this equation right here, which could be used to find the sum of an infinite number of terms in a series, if it's a geometric series, and if the common ratio from one term to the next is a fraction, so its absolute value is less than 1. In other words, it can be between -1 and +1, not including -1 and +1. And also, as I mentioned, that it was an infinite series. So in this example right here, the limit as n goes to infinity, so that would be an infinite series. For this, and this is a geometric series because we have something that looks exponential, a times b to the x power, and the answer is 12. And so what would x end up equaling? And is that a valid x? Does that x make it so in fact our radius or our ratio, our common ratio, is a fraction? Or is that x going to be a problem, because that would make our ratio be bigger than 1, and so then we would not have been able to use this equation. All right, so let's look at how we do this. So first of all, I'm going to assume, to start, I'm going to assume that I can use this equation. So I have my first term, which is when I plug 1 in for k, and so that'll be 6x. And I have 1 minus my common ratio. My common ratio is 2x. 1 minus 2x, and it equals to 12. So I solve it out, and I get my answer for x. Now, is that a valid answer for x? Well, okay, so in order to have used this equation in the first place, my common ratio has to be a fraction. So let's take that common ratio, which in this case is 2x, and let's say that it's my r, let's say it has to be less than 1, so I take the absolute value of 2, so I can pull that out and divide it. And so I need to have x's that are between -0.5 and +0.5. Yes, this x is good, so this is a valid answer. If my answer for the first part had been x equals 1, then I would have had to cross out that answer and say, in fact, there is no solution, because that x value was not within the valid range. So I would have had to discount it. In the second example, I have a series that has terms that have a common ratio between them. To get from one term to the next, I multiply by -x/3, multiply by another -x/3, etc. This means that I would take my -x/3, my common ratio, and it has to be a fraction in order to be able to use that equation for infinite geometric series. And so absolute value of anything negative becomes positive, and I can pull out my positive 1/3 and multiply it across. So I need to have x's that are between -3 and 3. This x is between -3 and 3, so I will get an answer. This x is not, so I can't use that previous equation, and the answer is that it diverges, or it just goes to infinity. Now in this last part, I have the answer for a sum, and I need to figure out what x value it is. Now that x value has to be, when I get that answer, it has to be in this interval right here. If it for some reason is outside of this interval, then the actual answer is no solution. So in part B, I take my formula, that's a1, or the first term, over 1 minus the common ratio, which is -x/3. I simplify, and I plug in 2 for my x value, so I have 3/3 and 2/3, that's 5/3, and I get my answer, and that answer is my final answer. However, if I had used x equals 4, and if I had plugged that in down here for x, well, I would have gotten another answer, and maybe I would have written that answer right there, because I would get something. But that's not the right answer, because this x value was not in the interval of convergence, so it will in fact not converge. The true answer would be diverge. In part D, I take my same formula, my first term, 1 minus my common ratio, just wrote it up there. I simplified it a little bit here, and I set it equal to the answer of 5, and I'm going to solve for x. I get my answer for x, but before I write it in the line, I need to look at that x and say, well, is that x one of my legitimate x's? If it is, then I keep it. If it is not, I will write no solution. Notice that the sum would not be no solution. That is a solution. It's infinity. So we would write diverge. But in this case, if I get an x that's an invalid x, I would not write diverge. I would write no solution. Diverge for sums, no solution for x's. For instance, in this problem right here, I have another infinite geometric series. My first term is 1. My common ratio is negative 3x. That's what I multiply by each time. So my little formula for finding the sum of an infinite geometric series, assuming that the r value is going to be a fraction, positive or negative, is here. So I plug in my first term, I plug in my r value, and I set it equal to 1/4, which is what we're told. And I solve and I get my answer for x. Should I write that x right here? Well, before I do that, I better check to find what my interval of convergence is for this particular series. And when I do that, and I take my common ratio, it has to be a fraction, minus doesn't matter in the absolute value, pull out the positive 3, divide it. Here's my interval right here between negative 1/3 and positive 1/3. This is not in there. So this x, although it's solved out, is not a valid x. It would in fact make this series diverge. It would not in fact get to 1/4 because we made this big assumption that we could use this formula, but in fact that was a bad assumption as it played out. So the actual answer is no solution. There's no way this infinite sum can add up to 1/4. In these next couple examples, we have a infinite geometric series which is geometric, but it's in disguise. It doesn't look like geometric right now, so we've got to sort it out to make it look geometric. Similarly, down here, we have a finite, 30 terms, a finite arithmetic series, but it doesn't look like that now, so it's in disguise. So we'll have to show that it is, in fact, arithmetic. You may be wondering why we go through this hassle of writing the limit as n goes to infinity and then put an n up here. Why not just go as I goes from 1 to infinity? And the answer to that is that it's not proper format. That on this sigma notation, mathematicians have determined that you're only supposed to put numbers, not directions like infinity is. So the only reason we don't do this is it's improper. All right, in this first problem, I'm going to pull apart this exponent and write it as 2 to the k times 2 to the minus 1. The reason being is that I can then join the 6 and the 2 to the minus 1. That's 1/2. So 6 times 1/2, and that's 3. And then also what I have left are 2 to the k and 3 to the k. So I have the same exponent, which is key, because then I can write 2 over 3 to the k. So I've gotten my numbers together, and I've gotten my exponents to the same exponents. I can put them together. Now I can see that I have something that looks exponential, a times b to the x, or geometric. And my first term would be when I plug in 1, so that'd be 3 times 2/3 to the 1 power, which would be 2. And my r would be 2/3. 2/3 is a fraction, so that means that I will get an answer when I have an infinite series of geometric, and my r would be 2/3, so 1 minus 2/3, 1/3, and I get my answer of 6. So I had to do a little bit of work. That's pretty common. In this case here, I have to remember my rules of logs. I'm going to trip and fall the k. There it is. Now I can either write it this way, or as we'll see a little bit further on, anything that is not, doesn't have a k in it, can actually come outside of the sigma notation without affecting the answer. I need to keep anything with a k on the inside. In this case right here, if I kept it like this, it would be 1 times ln 5 plus 2 times ln 5 plus 3 times ln 5 etc., etc. Here, the ln 5 is as if it's been factored out. And now I would just have 1, 2, 3, all the way up to 30 on the inside. Either way, obviously, I'm going to get that same answer. This is often a way to simplify problems and get rid of anything that is just cluttering up the situation. In this next example, we have a series which apparently is finite because we're asking for what the number is that goes up here. So this finite series that has an answer 6720. First of all, can I do like I just did previously and pull out the 2 because it has nothing to do with the k? No, I can't do that because I'm not factoring out the 2 just from the k. I would have to be factoring it out of the 3 as well. So you can only pull something out if it goes into both of them and you're factoring out. It's not a GCF. Second question, is this an arithmetic series? Answer, yes it is, because it has that linear look to it, mx plus b. Okay, so if it is arithmetic, then I can use my formula for the sum of a finite arithmetic series. I don't know the end value, that's what I'm trying to find, but I do know the first term by plugging in 1, 5, and I actually have a representation of the last term by plugging in n, 2n plus 3. I'm going to simplify by combining these, and I'll put the over 2, I can put it under the n, I can put it underneath this, I can put it underneath the whole thing. I'll put it here so that I could divide 2's everywhere, and distribute, and then I'll just have a regular quadratic that I had to use the quadratic formula because I couldn't figure out how to factor this thing. I got 2 answers. N has to be a positive number, so this negative number's out, and n is 80. So we'll take 80 terms of this arithmetic series before it adds up to this answer. In this next example, we have something that we're going to call a telescoping series, and there's a very good reason for that. And this is the old-fashioned type of telescope that was used on like pirate ships, that if you push from this end, it collapses up into this little tiny piece. That kind of telescope. First of all, I want to show you that you don't always have to start with k equals 1. In this case here, from 1 to 100, your first term would be 1 over 1 minus 1 over 2. But we could just as well write it with k equals 0 to 99. This would be the adjustment. And our first term would still be 1 over 1 minus 1 over 2. So it would be identical. So there's not a rule about where you have to start and end. It can be anything. So if I do several terms here, you can see what I'm getting when I plug in 1, and when I plug in 2, and when I plug in 3. And maybe you can see that there is some cross-canceling that can go on right here. In fact, every pair of terms will cross-cancel all the way up to that last pair. And then we will have this one extra term at the end. And this is very typical of what happens in a telescoping series. So basically you end up, after it has collapsed up, with just seeing the very front and the very bit on the back. Everything else crosses out. So in two-term summations that are not arithmetic, you should try to see if, in fact, when you plug in a few numbers, this is what's going to happen to it, make a common denominator, and get your answer.